and welcome to our presentation on the topic of managing big data stream pipelines using graphical service mesh tools. The authors of this paper are Mohammad Faizan and Christian Prehofer. So the overall objective of our research topic was to come up with a better management and controllability solution for stream processing pipelines utilizing graphical service mesh tools with Docker containers and Kubernetes as an orchestration tool. So we divided our objective into three subparts. The first part was to evaluate the management and execution capabilities of Apache Stream Pipes, which is a UI-based open source toolbox for stream processing. The second part of our research topic was to study the integration of service mesh tools like Istio with Apache Stream Pipes and find out the benefits of using service mesh in conjunction with Apache Stream Pipes in terms of management of pipeline execution. And the last part of our research topic was to implement a control layer on top of the system supporting various management scenarios like software upgradation or system migration and features like gradual shutdown of stream processing pipelines which could be helpful. So before we move forward, let's have a brief introduction of the tools and technologies we use in our architecture. So the first one is Apache Stream Pipes, which is a graphical management tool for creating, executing, and managing stream processing pipelines. It supports both real-time datasets and offline dataset as well, and it supports multiple protocols for the communication between the pipeline elements. It also comes with already built-in pipeline elements which you can use in your pipelines, or you can also implement your own custom pipeline elements using the Apache Stream Pipes SDK. The other tools which we use in our system includes Apache Flink, which is an open source distributed stream processing engine for stateful or stateless computations. For the communication between our pipeline elements, we use Apache Kafka, which is an open source distributed event streaming platform. And for the deployment of our stream processing pipeline, we use Kubernetes, which is an orchestration tool, and it allowed us in flexible scaling and management of containerized applications. And lastly, we also use Istio, which is one of the realizations of service mesh pattern. Service mesh allows us to manage service-to-service communication and gives us more features in terms of observability and security. So now coming towards the design and implementation of our stream processing pipeline, we use the use case of processing real-time data coming from connected electric vehicles. There are mainly three services in our pipeline. The first one is data pre-processing service, which receives the data from the connected vehicles and pre-processes and cleans it and prepares it to be consumed by the other services. The other services include driving behavior and power efficiency. Driving behavior, as the name suggests, estimates the driving behavior of the vehicle as good or bad. And the other service, power efficiency, calculates the vehicle specific power, which is the theoretical power the vehicle should have consumed. And it also computes the actual power the vehicle has consumed using the real-time data coming from the vehicle. Both of these services then stores the data or the final results in the databases, which is then visualized in real time on the Grafana dashboards. The layered system architecture is shown in this figure. Kubernetes is our primary deployment environment. Having the services deployed in a containerized environment allowed us flexibility in deployment, like easy provisioning of pipeline elements, scaling up or down Apache Flink task managers, or Apache Kafka brokers as needed. On top of Kubernetes, we have the service mesh layer provided by Istio and Envoy proxies using the sidecar pattern. One of the significant benefits of Istio is that it provides a secure communication channel between the pipeline elements, and it also gives us observability of what's going on in the system. For ease of creating and executing stream pipelines, we have deployed Apache Stream Pipes on top of the service mesh layer. And on top of that, we have implemented our use case services, which includes the data pre-processing, power consumption, and driving behavior service. On with the very top of our architecture, we have implemented the service management API, which provides us added features to manage the stream processing pipelines, like gradual shutdown of pipelines, also for software upgradation, and many other scenarios. As we have several complex tools and technologies involved in the overall architecture of our system, so we have done a systematic analysis of our system in order to define a clear responsible division of each component involved in our system. We have divided our system into mainly two layers. The above layer is known as the data layer. It includes all the tools which are involved in the creation, management, and execution of stream processing pipelines. It provides the execution environment for the business logic for the pipeline elements. And the below layer is known as the control layer. It provides all the controllability and management features for the deployment of data layer tools and technologies. For detailed overview of this responsibility division, please refer to our paper. For now, we can move towards the service management APIs, which we have implemented in the control layer to provide added features for the better management of stream processing pipelines. So as we already mentioned in the system architecture, that on top of the system we have implemented a service management APIs on top of the Apache Stream Pipes, Flink and Kafka, which provides REST APIs supporting different application level controls to internally communicate or interact with StreamPipe, Kafka, and Flink in order to perform different actions. And some of these actions includes checking the health status of the pipeline and also its individual components, which are the pipeline elements, starting or stopping the individual pipeline elements of the pipeline. And one of the major feature we implemented is the gadget shutdown of pipelines, which utilizes the concept of processing lag, which we will discuss in next slides. And later we will also show that how this procedure can be helpful in different scenarios like software upgradation and other maintenance scenarios, as in some cases it may take up to 18 seconds to properly shut down a pipeline for upgradation or migration. In the life cycle of any stream processing pipeline, a need may come to stop the pipeline due to maintenance reasons or any other reasons, and we can understand if we stop all the components of the pipeline at once, then we could lose the data present in the communication channels or in the buffers of the pipeline elements, which could result in inaccurate or unreliable results, which we don't desire in any real world application. So there is a need to follow a proper procedure to shut down a pipeline by simply first checking whether each individual pipeline element has completely processed the data present in its communication buffer or not, and if not, then we should wait until the pipeline element has processed all the data from its relevant communication buffer. So now the question is how to check whether a pipeline element has consumed all the data from its associated input buffer or not. So for that we have utilized the concept of processing lag, which tells us how much a pipeline element lags in processing the events available in its associated input channels or buffers. To calculate this processing lag, we have utilized the information from the Apache Kafka and Apache Flink regarding the communication channel and associated pipeline element. So the procedure we have devised and implemented follows a simple traversal approach. We start from the start of the pipeline, and for each pipeline element, we first check whether it has utilized all the data from its communication channel or not. If not, we will wait for it to complete, and then we stop the pipeline element and move to the next pipeline element. We do this until we have reached the end of the pipeline and the pipeline is completely stopped. Later, we will show you how such a use case can be beneficial in different scenarios for the maintenance or migration of stream processing pipelines. As we have just mentioned that we have utilized the concept of processing lag, now we will show you how such an information could be useful in seeing the performance of the pipeline elements, seeing how much load is on the pipeline elements, which could be helpful in scaling up or scaling down the pipeline, and also it could show you the effect of high event rate on the processing lag. So to do that, we have simulated multiple data streams at different event rates and plotted a graph among them. We have calculated uh, the rate of change in processing lag per second using this simple formula where we use the current processing lag, subtracts out the previous processing lag and divided by the change in time. We have done this experiment with different event rate, but we will only show you the two cases which to share the overall findings of our research. So here is the case one where we have the event rate of 3000 events per second, which is less than the Flink processing capability in our scenario. The first graph shows you the rate of increase in processing lag per second, meaning that how much processing lag is accumulating or changing per second in our system. And the below graph shows you the actual processing lag uh, value for each time interval. In this case, you can see that the change in processing lag is near to zero over the whole period of time, and also the processing lag in the system is also near to zero over the period of time. But you can notice one thing, that even the event publish rate is less than the Flink processing capacity. There are some peaks in this graph, meaning that there are some time where we have accumulated some data at the pipeline elements. Moving on to the case 2, where we have the event publish rate more than the Flink processing capability. Here you can see the rate of increase in processing lag is greater than zero, meaning that every second we are accumulating processing lag in our system, which is not a good scenario for production systems. You can see that after some time we have accumulated estimated 150,000 events for each pipeline element. So you can see that how the information of processing lag can be beneficial in seeing the actual performance of the pipeline elements, and we can then trigger out or fine tune our pipeline as needed. In the previous section, we presented the evaluation results with respect to processing lag in the pipeline, and we noted that even in cases of low event rate, there were some spikes in the processing lag, and if we stop the pipeline at these spikes, then we could have lost some events which could result in inaccurate results. So to cater for this loss of events, we presented a gradual shutdown procedure. Now we will take a look how this procedure can be helpful in use cases like software upgradation of migration. We have to stop the pipeline, upgrade it, and restart it. So again, we have done some experiments with different event publish rates. So the case one, where we have 3000 events per second, we ran 5 different runs and noted the complete pipeline shutdown time, and we can see that in this case we have the pipeline shutdown time uh, around 1 second. But if we now increase the event rate to 10,000 events per second and again compute the complete pipeline shutdown time, we can see that in this case we are taking around 20 seconds to shut down the pipeline completely. And this can be explained by one of our previous graph, where we showed that in case of high event publish rate, the processing lag was accumulated over the period of time, and this was not good for our system. So now coming towards the conclusions and contributions of our research work, we show that we have utilized Apache Stream Pipes to define, execute, and maintain stream processing pipelines with use cases from vehicle data analysis. Our first contribution is to design and evaluate the architecture of big data stream processing systems with a stack of widely used technologies, including Apache Flink, Kafka, and Kubernetes and Service Mesh Istio. Furthermore, we elaborated the responsibilities of our complex architecture and the role division of each component, and showed that how it could be helpful in development as well as in operation and management of such a system. Furthermore, we evaluated the pipeline management in our system, mainly on the case of processing lag and showing how it could be beneficial in production systems. And then also we evaluated our implemented gradual shutdown procedure and showed how it is crucial in big data pipelines, even in case of slow event rate. And also showed that in case of high event rate, this procedure can take up 20 seconds due to buffering in the system. But with the information of processing lag, we can fine tune our pipeline on the go and reduce it to around 1 second if they are operated on the lower data rates. Thank you for listening, and please follow us up for any questions.